In this chapter, we've been looking at general quadratic equations or functions which are of the form ax squared plus bx plus c. In the previous lesson, we talked about how to graph functions that are of the form ax squared. This time, we will try to answer the question, how does the value of c affect the graph of f of x is equal to ax squared plus c? So again, we will look at quadratic functions that are binomials, and they are of the form ax squared plus c. Last time, we talked about the transformations of quadratic functions by looking at the effect of a on the parent function x squared. We said that the sign of a determines whether the parabola is concave up or concave down. On the other hand, the value of a determines whether the graph is a vertical shrink or vertical stretch of the graph of the parent function f of x is equal to x squared. In this lesson, we will take a look at the effect of adding or subtracting a c to the parent function or to the function ax squared, and talk about vertical translations that are either upward or downward. So let's take a look at this slide. This is a summary of the effect or the effects of a on the parent function x squared. Now, what if the function looks like f of x is equal to ax squared plus c? So if a c or constant is added, the graph of ax squared plus c is a vertical translation c units up of the graph of ax squared. However, if c has a negative sign, then the graph of ax squared plus c, where c is negative, is a vertical translation c units down of the graph of ax squared. For example, graph g of x is equal to x squared minus 2, and compare the graph to the graph of f of x is equal to x squared. I'm going to skip the graphing part because we will talk about how to construct table of values later on. But for now, even before we graph the actual function, we can actually anticipate how the negative 2 will affect the original graph of the parent function. So since the value of c is negative, then we say the graph of g of x is a vertical translation 2 units down, because it's negative, of the graph of f of x. In the next example, we will compare the graph of g of x is equal to 4x squared plus 1 to the graph of f of x is equal to 4x squared. So take note that you are not comparing the g of x to the parent function. Instead, you are comparing g of x to the graph of 4x squared. So in other words, all we need to do is analyze the effect of positive 1. So how does positive 1 change the graph of 4x squared? So we learned earlier that if a constant is being added to the function, it results to a vertical translation upward. So let's write that down. So we say the graph of g of x is a vertical translation. How many up? We said 1 up. So 1 unit up of the graph of f of x. However, in the next example, we are asked to compare the graph of g of x to f of x is equal to x squared. So take note that this is the parent function, the original one. So that means we are going to discuss the effect of, first, 4, which was multiplied to x squared, and then secondly, the effect of positive 1, which is added to 4x squared. So these two questions are similar, but the reference graphs are different from each other. So how are we going to describe, and how do we know which ones to talk about first? Well, a general rule is we follow the rule of PEMDAS or GEMDAS. So since multiplication comes first before addition, then we're going to describe first how the 4 that was multiplied to x squared affects the parent function x squared. So how are we going to do that? So we learned previously that multiplying a constant that is greater than 1 changes your graph by causing a vertical stretch. So we say that the graph of g of x is a vertical stretch of the graph of f of x, which is x squared, and at the same time, adding 1 to the function causes the graph to move 1 unit upward. So let's include that as well. So the graph of g of x is a vertical stretch. Let me add also the factor that it was multiplied by. So let me rewrite the graph of g of x is a vertical stretch by a factor of 4. And a vertical translation, 1 unit up of the graph of f of x. So that's our complete answer to letter B. In this example, we're given f of x is equal to negative 0.5 x squared plus 2, and g of x is equal to f of x minus 7. The first question is, describe the transformation from the graph of f to the graph of g. So just to clarify any misconception, we are not describing the transformation from the parent function. What we're trying to compare is the effect of this constant, which is negative 7, to the original function, which is f of x. So how are we going to describe this? We said earlier that subtracting a constant causes the graph to vertically move downward. So let's write that down. The graph of g of x is a vertical translation 7 units down of the graph of f of x. So it's really important that you mention what your reference graph is. In this case, we're not using the parent function f of x equals x squared, but we're using the given, which is 0.05 x squared plus 2. So that was the original, and then g of x just subtracted 7 from the original function. So we said that it's a vertical translation 7 units down. However, in the next one, we're going to write an equation that represents g in terms of x. So what we're trying to do is we're trying to find a new function that represents g of x by combining the original f of x and the transformation that was applied. So in general, we know that g of x, let me just copy this down, is f of x minus 7. However, what is f of x? I'm going to keep copying and pasting just so you would see the transformation or the substitution going on. So we want to come up with another expression for g of x, and we want to get rid of f of x. So what is f of x equal to? We know from the example that f of x is equal to this whole thing. Let me copy this down. And I will use that to replace f of x in this expression. There you go. So now, if we simplify like terms, what are we going to get? So since negative 0.5 x squared is on its own, there are no more expressions that have x squared besides itself. We can just leave it alone. However, this one, positive 2 and negative 7 are both constants, so they are like terms. That means we can simplify them. So what is positive 2 minus 7? We get negative 5. So a new equation that represents g in terms of x is equal to g of x equals negative 0.5 x squared minus 5. Lastly, we're going to look at how quadratic functions of the form ax squared plus c represent some real-life scenarios and how they are useful in making predictions. Let's read the word problem. The function f of t equals negative 16t squared plus s sub 0 represents the approximate height in feet of a falling object t seconds after it is dropped from an initial height s sub 0 in feet. An egg is dropped from a height of 64 feet. After how many seconds does the egg hit the ground? So how are we going to use this function to solve for the time that the egg reaches the ground. So let's try to figure out some quantities here that we can replace. Let me copy this down so I don't have to write it all over again. So we know that the egg is dropped from a height of 64. So that's the initial height in feet. So that means we're going to replace s sub 0 by 64 feet. So plus 64. All right. And then the question is, after how many seconds does the egg hit the ground? So when the egg actually reaches the ground, what is the height? Well, from 64 feet, it travels for some time until it drops to the ground. So that means we're looking for the time in seconds such that after t seconds, the height is now 0. So when the height is 0, that means the egg is already, or the egg has already fallen to the ground. So how are we going to solve for the time in seconds, which is represented by the variable t? Now, does this equation look familiar? 0 equals negative 16t squared plus 64. So how are we going to solve it? That's the big question. Now let's copy it down here. And let's look at some possible scenarios. Well, first, it's a binomial. And by the way, when we say, how do you find the zeros or solutions, it's like getting the variable by itself. So pretty much, how are we going to find the value of t given this equation? So if we recall the factoring techniques that we learned in the previous chapter, we know that this is a binomial that has a GCF, and its GCF is given by negative 16. So if we divide both terms by negative 16, then we would get, let me just copy the t squared. There you go. And then plus 64 divided by negative 16. I should change the plus to a negative sign. So that's going to be minus 4. Okay. And we know that this binomial t squared minus 4 forms the difference of two squares pattern. So that means we can further break it down into negative 16 times t minus the square root of 4 is 2 times the quantity t plus 2. That means this equation has two possible solutions, and they are t equals, the opposite of negative 2 is positive 2, and the other possible solution is t equals negative 2. So in this case, we are only looking at the positive solution because we're solving for time. So we know that after 2 seconds, the egg has finally reached the ground. So that's just an example on the application of using quadratic functions in some real life scenarios.